In the previous lecture, we have seen about input delay max. Now let us see about input delay min in this particular video. So we already know like min input delay is used for hold analysis, and for hold this condition should get satisfied, that is arrival time should be greater than required time. So from here to data pin of flop is called as arrival time, and required time is something which is calculated with respect to the time period, followed by we will make use of either setup or else hold depending upon what we are calculating. That is, for max we will be going for setup and for min we will be going for hold. So at flop F3 in block B2, this is flop F3 in block B2. First let us try to calculate data arrival time, and these are some of the values which we have assumed. So time period is 10 nanosecond, source latency is 0.5, network latency is 0.7. As time period is 10 nanosecond, first triggering will happen at 0 nanosecond and second triggering will happen at 10 nanosecond. So that is rising edge is at 0 and falling edge is at 5, and next rising edge will be at 10. So you can see here clock rising edge. So here incremental delay is 0, so total delay is nothing but 0. Here active edge of reference clock is 0, that is rising edge is active. So first triggering is happening at 0 nanosecond and it is having an incremental delay of 0 nanosecond. Next clock latency, here you can consider this as source latency, which is nothing but 0.5 nanosecond. So total delay which is 0 plus 0.5 will give 0.5 nanosecond, and next it will have some network latency which will get added up. So 0.5 plus 0.7 will give 1.2. Next, in order to compute input delay, we have to give something called as set input delay hyphen min. So here this is something which will have clock to Q delay followed by combo delay C1 and combo delay C2, and this should be the min value. So input delay is something which is clock to Q delay followed by C1 plus C2. So from here till input port I1, how much time it is taking we have to give, and that should be the min value. So the value that we are taking is 6 nanosecond. So this 1.2 plus 6 will give 7.2 nanosecond. Here remember this point, for min and max we are taking the same value as 6 nanosecond. So we are done till here. Now we have to give the value of C3, means what is the combo delay C3. If it is max we have to give the max value, if it is min we have to give the min value. So that's why I mentioned here as min delay. So delay through C3 which I am assuming is 0.9 nanosecond. So this 0.9 nanosecond should be added with 7.2, so that we get 8.1 nanosecond as the total time the data is taking to reach to this particular data pin of flop F3. Means from this point till data pin of flop F3, total arrival time is 8.1 nanosecond. If you want to calculate it in terms of formula, you have to use this particular thing, which is clock source latency plus network latency followed by clock to Q delay, C1, C2 and C3 delay. Here clock to Q delay followed by C1 plus C2 is something which is called as min value, and it is something which is called as minimum input delay. So in our case it is 6 nanosecond. So I am taking a 6 nanosecond, whereas source latency and network latency we already know. Source is 0.5, network latency is 0.7. So substitute 0.5, 0.7. Next it is 6, which is clock to Q delay followed by C1 plus C2, which is min value, and next combo delay C3, which is also a min value, that is 0.9. So if we substitute all this, we will get arrival time as 8.1 nanosecond. Means from this point to data pin of flop F3 it is taking 8.1 nanosecond. As it is minimum, so it is something which comes under hold analysis. So for hold analysis this condition should get satisfied, that is arrival time should be greater than required time. So as of now from here to here it is called as arrival time, and the value that we got is 8.1 nanosecond. So if required time is greater than this 8.1 nanosecond, then there will be hold violation. If this condition is satisfied, there won't be any hold violation. Remember this point. So finally from this particular slide we understood we got data arrival time at flip-flop 3 D pin is 8.1 nanosecond. Now let us try to understand about data required time. So data required time is something which will be calculated in this manner. So these values we already know: time period, source latency and network latency. So in the previous case, while calculating arrival time, we have taken the first triggering is happening at 0 nanosecond. Now for hold also we need to consider the same. This is the important point that you need to remember. Current clock edge used for hold check. So same edge is used for hold analysis, so it is 0 nanosecond. Same edge is used for hold, whereas a different edge is used for setup. In the previous lecture we have seen like for set input delay hyphen max, first triggering is happening at 0 nanosecond and second triggering is happening at 10 nanosecond. But for setup analysis we will be using the second triggering, that is 10 nanosecond, whereas that is different in terms of hold. In hold we will be using the same edge, so that's why we are taking the triggering that is happening at 0 nanosecond. So incremental delay will be 0, so total delay which I got is 0 nanosecond. Next, we already know this is source latency, network latency, these values will get added up. So 0 plus 0.5 is 0.5, next 0.5 plus 0.7 will give 1.2 nanosecond. And here the important point is, as it is min, we'll be going for the hold analysis, and for hold analysis we are not dependent upon the time period, just we need to take the hold time of this particular flip-flop F3. So that's why I mentioned this figure here. In block B2 for flip-flop F3, from clock to D, there will be a time called as hold time, and these values will be present in our .lib. In upcoming videos, I'll be explaining you clearly about the different .libs that are present, like what is meant by NLDM, what is CCS, what is ECSM, and what is LVF.lib. I'll explain each and everything, and I'll show you from where you have to pick this particular hold time followed by setup time. As we are calculating hold requirement, we have to take some hold value that will be given from the .lib. So in our case, hold requirement is 0.3. So this 1.2 plus 0.3 will give 1.5 nanosecond, and there will be some clock uncertainty. So this 1.5 plus 0.2 will be added to get 1.7. So remember this point. In case of setup analysis, clock uncertainty is subtracted, whereas in case of hold analysis, it will be added. For hold analysis, there is no need of time period, whereas in case of setup analysis, total time period minus setup is something which we take. So if you want to do it in terms of formula, so required time is hold time plus clock uncertainty plus source latency plus network latency. We know this value 0.5 and 0.7, uncertainty is 0.2, and hold time from the .lib is 0.3. So add all this, you will get the answer as 1.7 nanosecond, which is nothing but data required time. So finally, in order to calculate the slack, it is something which will be arrival time minus required time. So from the previous slide, we got arrival time as 8.1 nanosecond. So 8.1 nanosecond minus required time which we got is 1.7. So if you subtract 8.1 minus 1.7, we get 6.4 nanosecond, which is something positive. So this condition is getting satisfied. Why? Because arrival time is greater than required time, so there won't be any hold violation. So slack is positive, so the whole timing on this part is met. If this condition is not satisfied, then here you will see something called as violated. If this condition is satisfied, you will see here something called as met. Remember this point. So this is the overall summary of set input delay hyphen max followed by min. So let's see this setup and hold. As I already told you, set input delay hyphen max is used for setup, and set input delay hyphen min is used for hold. So setup uses max delay C3, hold uses min delay C3. So here this is for max, this is for min. So for max, this C3 value will be max. For min, this C3 value will be min. So that's what this first point means. Next, setup uses the next clock edge, hold uses the current edge. I've already told you, for setup, we are calculating between 0 nanosecond and 10 nanosecond, means first triggering at 0, second triggering at 10. Whereas in case of hold analysis, same edge, that is 0 nanosecond is used for both. Next, coming to hold calculation, data required time is later than the clock edge. So hold value is added, whereas for setup, data required time is before the next edge, so setup value is subtracted. As I told you, for setup, total time period minus setup we take, whereas in case of hold, only hold time will be taken. Next, coming to the slack calculation, for setup, required time should be greater than the arrival time, so that's why it will be required time minus arrival time. Whereas in case of hold, it will be arrival time should be greater than required time, so it will be arrival time minus required time. Next, coming to clock uncertainty. So clock uncertainty is something which will be subtracted in setup analysis, whereas it is something which is added in hold analysis. So this is something which is the highlights of set input delay hyphen max followed by set input delay hyphen min. So please remember this particular figure, like why we are taking min delay for here and why max delay. So this is all about set input delay hyphen min.